Component form of a vector. Welcome, everyone. Today, we are beginning a very important topic in vector algebra, the component form of a vector. Now, as you know, when we first study vectors, we often look at them geometrically, as arrows or directed line segments that show both magnitude and direction. While that visual approach is great for understanding the concept, it can become quite difficult when we need to perform complex algebraic calculations or add multiple vectors together. To make our lives easier and our calculations more precise, we need a more structured way to represent them. That is where the component form comes in. This method allows us to move beyond just drawing arrows, and instead describe a vector using specific coordinates within a three-dimensional space. In the next few slides, we will look at the building blocks that make this coordinate-based description possible. The standard basis vectors. Now that we understand that vectors can be represented geometrically as directed line segments, we need a way to describe them using numbers. To do this in three-dimensional space, we first define three special unit vectors that act as the building blocks for all other vectors. In mathematics, we refer to these as the standard basis vectors. If we look at a three-dimensional Cartesian coordinate system, we have three specific directions to consider. First, we have I hat, which is the unit vector pointing along the x-axis. Next, we have j hat, which is the unit vector along the y-axis. And finally, we have k hat, which is the unit vector along the z-axis. Now, it is important to remember the term unit vector. A unit vector always has a magnitude of exactly 1. Because their magnitude is fixed at 1, the primary purpose of I hat, j hat, and k hat is to simply provide the direction of their respective axes. This sets the stage for our next slide, where we will see how we can use these building blocks to define the position of any specific point in space. The position vector. First, let's consider a point, which we'll call P, located somewhere in our three-dimensional space. To locate this point precisely, we use its coordinates, which are x, y, and z. Now, here is the key concept. If we draw a directed line segment starting from the origin, which we denote as O with coordinates 0, 0, 0, and ending exactly at our point P, we have created what is known as the position vector of point P. In mathematical notation, we represent this specific vector as P with an arrow over it, or more simply, as the letter R with an arrow over it. This vector essentially tells us how to move from the origin to our destination in space. Now that we have introduced our building blocks, the standard basis vectors I hat, j hat, and k hat, let's see how we can use them to pinpoint a specific location. Expressing a vector in component form. Think of the position vector, r, as a single diagonal movement through space. However, we can actually break this single movement down into three perpendicular parts, where each part corresponds directly to one of our coordinate axes, the x, the y, and the z. This allows us to write the component form of the vector as r equals xi hat plus yj hat plus zk hat. To really understand what this expression is telling us, let's perform a step-by-step breakdown of each term. First, the term xi hat represents the projection of our vector along the x-axis. It tells us how far we move in the horizontal direction. Second, the term yj hat represents the projection along the y-axis, showing our movement along the second axis. Third, the term zk hat represents the projection along the z-axis, which accounts for our vertical movement or height. Finally, when we take the sum of these three orthogonal, or perpendicular, vectors, we arrive back at our resultant position vector, r. Essentially, we are just reassembling those three individual directional movements to reconstruct the original vector. Now that we have defined our position vector as the line connecting the origin to a point in space, let's look at how we can actually write this vector down mathematically. In the next slide, we will clarify a very important distinction between the numbers we use in this formula and the actual vector terms themselves. Scalar components versus vector components. Now that we have seen how to construct a position vector using the standard basis vectors, we need to be very careful with our terminology. It is easy to use the word component loosely, but in mathematics, it is important to distinguish between the scalar and vector parts of the expression. R equals x I hat plus y j hat plus z k hat. First, let's look at what we call the scalar components, which are also known as the rectangular components. These are simply the real numbers x, y, and z. Think of these as the instructions or the magnitudes along each axis. They tell us how far to move and in which sense, meaning whether the direction is positive or negative along the x, y, and z axes. On the other hand, we have the vector components. These are the actual terms xi hat, yj hat, and zk hat. Unlike the scalars, these are actual vectors themselves. Each one of these terms represents a directed line segment that points specifically along the x, y, or z axis. Understanding this distinction is crucial, especially as we move into our next slide, where we will apply this exact logic to a real-world scenario involving a drone's flight path. Real-world example: tracking a drone. Now that we have understood the theory behind position vectors and standard basis vectors, let's put everything we've learned into a practical context. Imagine a drone taking off from a launch and pad, which we will treat as our origin. Point O, the drone flies through the air to a specific position, which we'll call point P to get there. It travels 3 meters east, which corresponds to our x-axis, 4 meters north along our y-axis, and finally, it climbs 5 meters upward along our z-axis. To represent this movement mathematically, let's follow a 3-step process. Step 1. First, we need to identify the coordinates of the point. Based on the distances we just mentioned, the coordinates of the drone's position, point P, are simply 3, 4, 5. Step 2. Next, we identify the scalar components. As we discussed in the previous slide, these are the real numbers that tell us the magnitude and direction along each axis. In this case, x equals 3, y equals 4, and z equals 5. Step 3. Now we write the vector in component form. We will use the formula we learned earlier, where r equals xi hat plus yj hat plus zk hat. By substituting our specific values into this formula, we get the vector r equals 3i hat plus 4j hat plus 5k hat. To wrap up this example, let's be very precise with our terminology to avoid the common mistakes we will discuss in the next slide. In this expression, the terms 3i hat, 4j hat, and 5k hat are our vector components, while the numbers 3, 4, and 5 are our scalar components. Common mistakes to avoid. First, let's talk about the distinction between scalars and vectors. As we discussed in the previous slides, it is a very common mistake to say that the component of a vector is simply x. While we often use these terms interchangeably in casual conversation, in mathematics, precision is key. To be mathematically accurate, you must remember that x is the scalar component, whereas xi is the actual vector component. Always keep that distinction in our mind when writing out your final answers. Second, please be careful not to ignore your signs. When we are working in 3-dimensional space, direction is everything. If a point is located in the negative direction of an axis, for instance, if a point is 2 units behind the origin on the x-axis, your scalar component must be negative 2. Forgetting that negative sign will change the entire direction of your vector, which would lead to a completely different position in space. Finally, a quick practical tip: always check your units. If you are working on a problem where one measurement is in centimeters and another is in meters, you cannot simply plug them into your formula. Ensure that all your components, x, y, and z, are expressed in the same units of measurement before you write out your final vector form. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. Even if you understand the concept of the drone example we just looked at, it is very easy to make small errors that can lead to incorrect answers in your exams. Once you have mastered these 3 points, you will be well prepared for our final summary of the key takeaways. Key takeaways. First, remember that the unit vectors, which we denote as I hat, j hat, and k hat, are our essential building blocks. They are special vectors with a magnitude of 1 that serve to define the specific directions of the x, y, and z axes in our three-dimensional space. Second, we learned how to represent the position vector of any point. Let's call it point P with coordinates x, y, and z. We can write this position vector, denoted as r, as the sum of xi hat plus yj hat plus zk hat. This formula is what allows us to translate a simple location in space into a mathematical expression we can actually calculate with. Third, it is crucial to keep your terminology precise, as we discussed in our section on common mistakes. Always distinguish between the scalar components and the vector components. The scalar components are simply the real numbers, the coefficients, which are x, y, and z. On the other hand, the vector components are the actual terms that include the direction, specifically xi hat, yj hat, and zk hat. All right, we have reached the end of our lesson on the component form of a vector. Before we wrap up, let's quickly recap the key takeaways to ensure you have a solid grasp of the fundamental concepts we've covered today. If you can keep these distinctions clear and apply them to your calculations, you'll be well on your way to mastering vector algebra. Great job today.